We humans have a great sense of touch, which helps us to feel things around us. Our goal is to give robots a similar sense of touch by creating artificial tactile skins. We introduce a way of creating soft and high-resolution tactile skins with a few inexpensive components. A common way to achieve high-resolution sensing capabilities is to integrate a large number of sensing elements. It requires many components and numerous wires. We pursue a way that only uses a few sensing elements, called taxels, and advanced data processing to achieve the same sensing performance. This is called super-resolution sensing. While creating different skin prototypes, we observe that several taxels respond to the contact on the soft skin, each of them in a different manner. To understand this more deeply, we closely look at one of such taxels, on the right. The taxel has a certain response when touched directly above it. To keep this particular response, we need a higher force when the contact points are further away. The orange line describes this force-distance relationship, called taxel value isoline. How can we make use of these isolines? Consider two taxels and their isolines. The point where they meet tells us the contact location and contact force, shown in green. However, we always have measurement noise, visualized by the blue shaded area. Thus, a contact point can only be inferred up to a certain precision, visualized by the size of the dashed square. Comparing how many points we can distinguish, the number of dashed squares, to the number of taxels, the orange squares, gives us a measure of performance, the super-resolution factor omega. We aim to design sensors with a super-resolution factor as high as possible. When creating sensor prototypes, we are always confronted with many design choices. For instance, which taxels should we use? Barometers, accelerometers, or something else? How thick should the skin be? How far can the taxels be spaced? And where should the taxels be positioned within the elastic material? Last but not least, which material is actually appropriate? Our theory can be used to give informed answers to these questions to obtain optimal super-resolution sensing. Using our theory as a guidance, we created a patch of tactile skin with a grid of only 5x5 barometers by optimizing all these aspects. After building the sensor prototype, we used a deep neural network to infer the location and force of a contact point from the readings of the 25 barometers. We built an automatic testbed to collect the data and train the neural network. The network then maps the sensor readings directly to the contact location and force strength. Our prototype has astonishing sensing capabilities. We illustrate the precision by letting the testbed stimulate the skin following the points constituting the Minerva picture. Already for a contact force corresponding to 50 grams, the skin can localize contact very precisely, shown by the green dots. Almost perfect reconstruction can be obtained for 100 gram contact. It can distinguish more than 25,000 points using only 25 taxels, which means a super-resolution factor of over 1,000. Besides, the prototype can measure the contact strengths very accurately. We hope that our findings will help the community to develop great sensors and give robots a robust and dense sense of touch. We are Hanbo Sun and Georg Martius from the Max Planck Institute for Intelligent Systems in Germany. Thank you for watching.